Hi everyone, I'm Katrina Ravichandran and this is Elaine Chen, and today we're presenting our project, Reusable Influenza Detection System, which combines acoustic wave modeling and Raman spectroscopy to detect airborne viruses like influenza in a fast and non-invasive way.
We'll first start with a quick overview, followed by our abstract and a little introduction, our goal and scientific concepts, our methodology, acoustic wave and Raman processes, and then we'll go over our results and visual outputs. And then we'll finally end off with a conclusion and ideas for our future research.
And here's a little overview of our abstract. And to start off we'll start off with an introduction. So, in recent years, we've seen just how devastating airborne viruses can be. COVID-19 alone has claimed over 7 million lives globally. But even beyond pandemics, seasonal influenza affects nearly a billion people every year, with up to 5 million serious cases annually, according to the World Health Organization. And these statistics highlight the urgent need for better tools to detect viruses early, before exposure or symptoms begin.
Now let's look at the limitations of current virus detection tools, like rapid test kits. Most of these solutions must be thrown away after a single use, making them both wasteful and costly at scale. They also require physical contact, like swabs or blood samples, which isn't ideal for fast or widespread deployment. Crucially, they only detect viruses after infection has already occurred and often after symptoms began. This means they offer no real-time monitoring and no early warning system to help people avoid exposure in the first place. And that's the gap that our project aims to address.
So to reiterate our goal, we aim to create a reusable real-time detection system that identifies influenza particles in the air before infection occurs, allowing people to avoid high-risk environments proactively.
Now let's break down two core technologies that we used, starting with acoustic waves.
So acoustic waves are defined by amplitude, wavelength, and frequency. So we can adjust these parameters in order to control how particles move, which allows us to isolate smaller virus-sized particles from the rest of the particles.
This table shows particle response under acoustic influence. Influenza particles are displaced differently compared to other particles like dust and pollen, enabling us to have size-based filtrations with acoustic waves.
And once we isolate these virus-sized particles, we use Raman spectroscopy to identify them based on molecular fingerprints. So most light usually scatters normally, which is called Rayleigh scattering, but there are some shifts in energy due to molecular vibrations, which is called Raman scattering. And these shifts are unique to each molecule, and that helps us detect proteins and lipids in viruses specifically. And the Raman shift formula tells us how much the light's energy changes, helping us locate its peaks in inverse centimeters. For influenza specifically, we look for strong peaks at 1,600 and 2,900 inverse centimeters, which are markers of proteins and lipids.
Our Raman system focuses on these components. Virus-positive samples consistently show peaks at 1600 and 2900, while virus-free samples show background peaks at 1200 and 2500 centimeter inverse. This spectral contrast makes classification reliable.
And now let's walk through how we simulated this process, starting off with the acoustic wave modeling.
This slide shows our acoustic wave simulation that we built in SlideLab. We use a sine wave generator to model acoustic vibrations, and the values shown represent physical parameters like wave speed and particle mass through the second order function. And through integration, we can calculate the particle displacement over time, which helps us visualize how acoustic waves influence particle motion in air.
So we modeled this displacement of different particles using the second order transfer function, where A is equal to the mass, B is the damping from Stokes's law, and C is the restoring force from Hooke's law.
We implemented this equation in Scilab using block diagrams. It allows us to simulate particle behavior under acoustic influence based on their physical properties.
Then we focus on extracting time and displacement data from the simulation for different particles and especially influenza. And this let us compare how each type responded to the same acoustic waves being generated for all of them.
Now for our Raman modeling side of our methodology.
So we started by identifying the two key Raman shifts associated with the influenza virus, which is around 1600 inverse centimeters for proteins and 2900 inverse centimeters for lipids. And these act as our anchor points for generating virus-related spectral signals.
Next, we use the Gaussian function to model these peaks mathematically. This formula lets us control peak intensity, center, and spread, mimicking how actual Raman spectra will appear in real measurements.
And to make the simulation more realistic, we added random noise using NumPy's normal distribution function. And this step simulates the imperfections you'd see in real-world Raman data due to environmental factors or device variation.
We then combined the synthetic peaks and noise to build full spectra. Using a peak detection algorithm, we extracted the most prominent peak positions, just like how real instruments would detect and label Raman shifts.
And from the detected peaks, we selected and normalized the top five intensity values. These served as our AI input features, allowing the model to focus on the most informative parts of the signal.
Finally, we use these features to train a neural network to classify samples as either virus present or virus free. The input layer receives five intensity values, then passes them through hidden layers and outputs a prediction that's binary of virus or no virus.
And now let's take a look at how this works in our actual device model.
Here's a look at the front of our prototype. Air enters through a fan at the top, carrying airborne particles into chamber 1. This chamber uses selective acoustic waves produced by a piezoelectric transducer to manipulate particle movement. Then a precise, timed opening allows only particles in the virus size range to pass into the second chamber, where detection happens. In the second chamber, a Raman laser and a sensor scans the particles for virus-specific peaks. Once detection is complete, a UVC sterilization cycle activates to sanitize the chamber before moving on to the next reading.
On the back, the system is powered by a lithium-ion battery pack, making it portable and independent of wall power. And the processing is handled by a Raspberry Pi microcontroller, which runs both the AI model and interfaces with the Raman sensor. This setup makes the device compact, programmable, and ideal for future integration with mobile apps or alert systems.
Now let's go over our key results.
Our simulation shows that influenza particles move more under acoustic waves due to their smaller size and lower resistance, and that allows for real-time physical isolation of virus particle sizes.
In this simulation, the yellow dot represents nanoparticles, which disappears quickly because the acoustic waves makes them travel really far in a short amount of time. But later on, the blue particle represents our influenza virus, which travels further while the other more heavy particles remains at rest. During that time where the blue particle travels all the way to the end, that is when our chamber door will open and isolate the influenza particles so that it can go to the second chamber to be detected. Here we see the displacement graphs of two particles, one representing influenza and the other dust, under a constant acoustic wave. The graph on the left shows minimal movement from the heavier dust particle. Meanwhile, the graph on the right shows a clear upward displacement curve for the influenza particle. This confirms our hypothesis. Virus particles, because of their smaller size and lower resistance, displace significantly more under the same conditions. This physical difference makes it possible to filter virus-sized particles using acoustic forces.
And we also use Raman spectroscopy to distinguish between virus positive and virus negative samples based on molecular signatures. On the left, the red virus positive line shows clear peaks at 1600 and 2900 inverse centimeters corresponding to protein and lipid bonds in the viral envelope. The blue line shows a virus-free spectrum with smaller unrelated peaks caused by background noise. On the right is a new sample. Our AI model correctly identifies the virus positive by matching those same 1600 and 2900 peaks. This distinct pattern is key for reliable classification.
Now, looking at our model's accuracy, our classifier achieved 90% accuracy overall. The virus present class has a precision of 0.95 and a recall of 0.86, meaning it was very good at identifying true positives. The no virus class was slightly less accurate due to a few false positives. The confusion matrix shows we correctly identified 96 virus positive and 84 virus negative samples. There were 15 false negatives and only 5 false positive, supporting our model's reliability in practical use.
And these final graphs show how our model improved through training. On the left, we see accuracy steadily rising over 35 epochs for both training and validation sets. This suggests strong generalization. On the right, the training and validation losses both drop sharply, then level out. Validation loss stabilizes after about 15 epochs, showing how our model is well tuned and avoids overfitting. This consistent learning curve reflects the model's robustness in detecting viral signatures from Raman data.
So to summarize, acoustic waves isolate virus-sized particles in under 3 seconds, and our Raman and AI models detect viral signatures. Our system achieves 90% accuracy quickly and contact-free.
So overall, this approach enables real-time contactless filtration and detection of airborne viruses with potential applications for more than just influenza.
Our next steps for future research are to validate our research with real influenza samples in a lab setting. We also want to retrain our AI models on real-world data and simulate realistic droplet conditions, putting into account of fluid dynamics. Then we want to optimize manufacturing and expand to other viruses by tuning our acoustic wave parameters.
And now here are some of our references.
A few more, and these are our image sources. Thank you so much for your time and your attention.